Okay. So we are going to start on page 142, I believe. Correct me if I'm wrong, y'all. And we're going to finish up the notes there. Yes. And yeah, should we start with that? Taylor, what do you have a particular question in page number? Let's start there before we chapter 4 review. Okay. What one do you want to look at? Okay. So we cannot state that fat intake, keyword there, causes cancer. So my first question, anytime you see this thing, this word cause or causation, you should ask yourself, what type of study is this? So this is the relationship between the average fat intake per capita per day in grams and the death rate per 100,000 people of colon cancer. So there are two types of studies. Is this a designed study or an observational? Or you don't know?
My guess is observation.
Okay, great guess. Why do we think it's observational? Or do we know the difference between the two?
Design experiment is manipulated by the researchers.
Love it. Yeah. So there's some form of manipulation. We might call that a treatment. There's we break the sample into at least two groups, maybe more, and there's a control group and a group that gets the treatment, and we mess with things. So if you think about what's happened here, this would be impossible to design. You've got what, a bunch of countries, and we're going to say, okay, everyone in Thailand, you are limited to this much fat intake per day per capita, and everyone in Netherlands, you get to eat this much fat per day, or you have to eat this much fat per day, and let's see who dies from colon cancer. Right? So this is an observational study. Now, once we know it's observational, what then does that say about any of our results? So, by the way, the result we've noticed is that the more fat intake a country as a whole, that's what per capita is more or less talking about, the more fat people consume, the more people that die from colon cancer. That's essentially our claim. That's the claim here, that fat intake causes, we should say colon cancer, but whatever. So we've stated it's observational. That's true, that's correct. We just collected a bunch of data and we're reading what the data says. Why can't we claim causation? I'm going to highlight something just for fun. Fail. I failed in that highlight.
There's other factors like genetics and stuff like that.
Yes. Anytime we have an observational study, what we're finding is a correlation between the two variables. So there is a relationship between fat intake and colon cancer death. As one goes up, the other goes up. Is it the fat intake that causes it, or is it something else? We don't exactly know. It could be fat intake has a role in it, but we don't know. So the answer is we cannot claim it because this is an observational study, which means we can only claim correlation. And the reason we can only claim a correlation is because there are lurking variables such as ... I think we talked about this in the night class, but we haven't talked about it here. Anytime you're talking about health things, Cindy pointed out, maybe she told this to you already, genetics is a great option of a lurking variable. My grandmother was a vegan, like never smoked or drank anything in her life, like a perfect model of health, and she died from pulmonary fibrosis. No, she died, her lungs stopped working. There's some, I forget the name of the disease, but she never, like, she did all the right health things. And then I have another, someone I know who smoked all the time and lived longer and didn't die from lung cancer. So maybe genetics, right? So there's all kinds of different things you could list here. The key thing I'm looking for is that you connect the observational study with correlation not being causation, and that the reason correlation doesn't make that strong statement is because of the other options that we couldn't control for, those lurking variables. And then you suggest one. So Taylor, what did you think for E? If the fat intake increases, so that means if we're going in this direction, what appears to be happening to the death rate? What was your thought? Oh, yeah. You put E and you nailed it. Number 2E, I guess I can't read. Oh, excellent. What are the two things then that need to make something influential? There are two things that have to happen to a data value. By the way, the one we're talking about, of course, is this one, the US's data value. Anyone remember those two things? One starts with an L and ends with an average.
The leverage and the residual.
Nailed it. Okay, so we need to see leverage happening and we need to see residualness happen, meaning there needs to be lots of it. So leverage is the distance on the x-axis. That's lots of leverage, right? Residual is the distance between the data value and the line. Is that lots of residual?
Not very much.
Right? It's pretty close to the line. That's a small residual. So your answer here is it's not influential because the residual is small. To be influential, the value would have to be somewhere over here, because then you have a large leverage and large residual. Let's see, Taylor, what was the other one? G. Oh, the slope. This is that one we were working on. How are you? Oh, and what? So how do we find the slope? What do we look for? What should we put for E, y'all? The question is, was there a high amount of leverage and high amount of residual? If there was, we would say yes. If there is not, we would say no. So do we think there's lots of both? Oh, you do think there's lots of residual? I disagree, respectfully. Residual is that distance between the data value, so here's the data value we're talking about, and our predicted data value, which is the number on the line. So this distance, that amount is way less than this amount. And it doesn't quite matter that it's less. We just need lots of that for it to be an influential point. And doesn't have lots of residual. It's relatively close to the line. Good. Yeah, Laura, that's a good point. Yep. Leverage, check, lots of leverage. Residual, nope, not very much. In fact, if we look here, this residual is actually worse for this data value. This one right here, that's a longer line. It's still not too bad. But that the leverage on this one, there's like zero leverage for that data value. Yeah. Taylor, do you feel like do you feel like that makes sense for E? You know what to write? No, because the residual is low, is one way you could say it. Or the residual is small. Explanatory variable is the x-axis, swamp. Response variable is the y-axis, swamp. So that sentence goes there, or that thing goes there, and that one goes there. Awesome. Did you all say like 25 or 26 here, by the way? You counted all the dots, and that's roughly what it was. Okay, G. Taylor, what's the slope? Do you know that? Or anyone? I know, sorry, Taylor, it's like I'm picking on you, but anyone know what the slope is, or where to find it, or how to find it? I forget. Close.
0.0866 because it's
So-
next to the X.
Nailed it. That's what I want to hear. Excellent. Reagan. I was thinking Reagan. I remember you didn't care, but I want to do it right. Yes, always think slope is next to X. Now remember the problem we have here is that our textbook and your reference sheet writes it like this, and StatCrunch writes it like this. So, you know, keeping track of where the slope is and where the y-intercept is, that's important. So yes, it's the number times X. So it's at 0.0866. How's everyone doing with that? For the sentence structure, I kind of don't want to write it. I want to make you do it because it's already written right here. You just have to put in the stuff. And if we look at, what page number is this? If you look at what we have already labeled, here's X for the quote marks in your sentence structure. Here's Y for the quote marks in your sentence structure. The units are firearms per 100 people for X. The units for Y is a death rate per 100,000 people. And A is this. So you just smash those pieces in, the words here, the number here, and you got it. Is that okay? Is that enough for you to feel like you can do it? I also don't want to answer N because N is right here. This is N. So you're going to put in the words for Y that we already wrote above. You're going to convert that R squared number to a percentage. It is a decimal, so convert it to a percent, and you got it. Let's see, is H the same thing? H is similar. I'll go back to page 263. So H is this. And yes, it's very similar. the answer, what you write for X here is the same as what you wrote for X here. What you write for Y on this one is the same thing you're writing for Y here, which is the same thing you're writing for Y there. The difference here is that you're using the Y coordinate of the Y-intercept to list it. And don't forget, when you write out the Y-intercept, when you state it, it's got to be 0, B. Now, I think the thing that makes H different is it doesn't say interpret it, does it? What does it say? H says explain why the Y-intercept does not make sense. So that you have to look at your values and make sure and think about contextually, can one thing happen? Can you have a 0 and the other number? So it might help if you write out the interpretation. Nailed it. That's right, Taylor. It's don't forget though, it has to be 0, that number. That's the part that most people get wrong. Okay. Let's see. Let me make sure I've answered. We talked about G. We talked about B and C. We talked about N. Those of you that asked for those questions in E and G and F, do you feel like you have been given enough assistance to do them, or are you still stuck? Also, I'm aware I'm not actually telling you the answers. That's kind of on purpose. I'm taking, you're like birds and I'm letting you fly, right? You're spreading your wings, and I might be the wind beneath your wings, like that one song that someone sang once. It's okay to get lost. Don't you worry. That's why you ask questions. Yes, I'm kicking you out of the nest. I just saw an article that in the Netherlands, they take some sort of penguin and they throw them off the cliffs. It was on NPR. I don't know if you all saw that. And it was because humanity has, the lights make it so they can't find their way to the cliff to fly off into the ocean. And so the people are throwing them off so that they can find their way out to wherever they're supposed to go. It's kind of nice. They're trying to correct their wrongs. They could also just turn off their lights, but whatever. Cool, good. Please keep asking questions. Let's make this happen. So I'm going to go to 142, and we're starting here, I believe, in your notes. You all correct me if I'm wrong. We're going to draw a tree diagram and do the sample space for a family having 3 children. And we're looking at the biological sex of the child, and we're assuming a binary option. So we're making 2 assumptions that aren't scientifically real at all. Number one, that there is only a binary option at birth. And number 2, that there's a 50-50 chance of males and females being born. We can look empirically at these chances, and I forget, it's pretty close to 50-50. I think I looked it up once, and there's slightly more females born than males in US hospitals, but whatever. Okay, so are we all on the same page 142?
I'm there.
So, tree diagram. Let's do it. Love it. First note that what we're doing here is we've got 3 options happening. So we're going to do this basic starting point, and we're going to say, okay, a couple comes together, they do their thing, they conceive a child, they go to the hospital, and they give birth, and this is what could happen. We could have, let's alphabetize it. So we could have the child born female, or we could have the child born male, based on the assumptions we've made in the problem. And we're assuming that's equally likely. So this represents the first child, child 1. By the way, the goal of this tree diagram is to create a sample space. not to draw the tree. Like the tree is supposed to help you create the sample space. All right, so child 1 is born. The couple wasn't satisfied with one child. They're a glutton for punishment, right? And they don't care about money, so they work together to get another child. And so we have, again, female, male. This is assuming that the first child was female. This is the option that could happen. If this isn't true, then we'd go down this branch and we could have female, male. Maybe the first child was like the easiest baby ever, and they slept through the night and they didn't realize what terrors children can be, right? Child 2 happened, so this is the sample space for having 2 children. Well, then, you know, as the story can go, someone forgot their birth control, I'm assuming is what happened here. Just kidding. Lots of people like lots of children. So here we come for the third child, and same thing. We could have female, male. Female, male. By the way, while I'm writing this out, does anyone know the calculation? Have we done that already in the notes? Nope, we're about to get there. Never mind. And then this is how we can construct the sample space for a family of 3 children. And the way we read it is we start at the beginning. Oh, let me write this. This is the third child, child 3. We can start and just follow the branches and count out the children. So I'll do that in whatever this color is and say, okay, so one option is we could have a family of 3 females, 3 female children. That's that first one. Well, we could have the first 2 being female, and then that last child was male. That would be here. Or we could have a female, male, female. How are you all doing with reading these tree diagrams and putting them together? Is it making sense, or is it kind of craziness? Like when we count these last branches, this is the total number of outcomes. 1, 2, 3, 4, 5, 6, 7, 8. We'll have 8 outcomes in our sample space. We then, I'm like totally not waiting for your responses. Maybe you're just busy writing or drinking coffee. Okay, so we've now written out all the options where the firstborn is female and then the rest happen, right? Now we're going to look at the firstborn being male. So that I start here and I read along this way. Shoop, 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 shoop. So male and then 2 females. And then male, female, male. And that takes this one. Male, female, male. And then male, male, female. And male, 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 male. I think I did too many males there. And that's the listing. So I did this one, and I did that one. And then we could count this, and there's 1, 2, 3, 4, 5, 6, 7, 8. This is the sample space. And this was the whole point of drawing the tree. The tree itself is not the goal. It's to write out the sample space, because it's often the most important thing we need with probabilities is how many outcomes are there, what are those outcomes, and what's the probability of each of those outcomes happening. Should I pause there, or should I just keep flying? Okay. So we assumed here that that the male female outcome, or the male female option, was equally likely. So then we're saying, all right, in a 3-child thing, what do we assume is the likelihood of the 3 children? So each of these 8 outcomes has a 1 in 8 chance of happening. So we're going to assume that they're all equally likely. And that's because each individual thing was equally likely. And so that probability of any outcome, we'll just say outcome, is a 1 in 8 chance. if you ever study conception, I haven't studied a lot of it, but I've heard some of the science behind it. It is like a crazy, like the fertilization of the egg and all that goes into that is insane. I think it's close to miraculous. Science has a hard time explaining all that goes into it. So this is an overly simplified look at genderizing a child. All right, so then we get this thing. So one outcome in the sample space is one of these 8 things. This says having at least one male. Now this word is super important. At least means 1, 2, or 3 males. 1 or more. So when we look at our potential outcomes up here, we're going to list the ones here that have M in it. And if you look at it, it's everything but the very first one. So the list of outcomes for that event, we could almost call it the sample space of the event, is F, F, M, F, M, F, F, M, 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 F, F, M, F, M. That's funny letters, M, M, F, and M, M, M. If you want to be super precise in how you write these things, we often use these little squiggly brackets to talk about this is the set of outcomes from event H. So if we want to state the probability, remember where you defined this earlier in the notes, the probability is the number of outcomes in the event. So I'll just put number of events divided by the by the total, the sample space. So there are 7 options in event H, and there are 8 total options in our full sample space. So we have a 7 in 8 chance of having at least one male being born. Wasn't it King Henry that like wanted a son for a king, and he kept having wives and he kept killing them all because all he would get was a daughter? Was that the king? Henry VIII or something? And isn't the biological sex of a child determined by the male stuff? So he should have killed himself. Okay, so the tree diagram above worked well for 2 and 3 children, right? That's not too terrible. But what if we wanted 6 children? Yikes, right? Because child 4, we're getting here, and this is getting gross already. And then we still have 2 more after this. And if you think about what's happening here, we went from 8 outcomes to now 16 outcomes. And then if we try to draw the tree diagram stuff off of this, we're going to go from 16 outcomes to 32 outcomes, and that gets us 5 children. And then if we go from 5 to 6 children, we're going to go from 32 to 64. So the very end of our tree diagram is going to have 64 branches on it. So we just say like gross, too much work. And as often is the case in math, we're like, surprise, there's a shortcut. If you want to know the sample size, not the individual outcomes, but how many total outcomes, which by the way is super important because we need that number as our divisor, all you have to do is multiply together the different ways that each individual outcome could happen. So if we think about what we just did, we had the first child, there were 2 possible options for what could happen for that child. And then for the second child, we had 2 options. And for the third child, we had 2 options. And if we multiply these together, we end up with a total of 8 possible outcomes. That's what this thing is saying. If we want to calculate the sample size, we just multiply together the different ways that things could happen. So In example 10 here, we're like, all right, with these 6 children, how many possible outcomes? I already told you the answer, but let me write it out slow wise. So child 1, child 2, child 3, child 4, child 5, and child 6. 2 ways we could pick the first child, 2 ways the second, 2 ways for the third, 2 ways for the fourth, 2 ways for the fifth, 2 ways for the sixth. We're going to multiply these all together. If you know exponents, that's like repeated multiplication. We have 6 2s we're multiplying together, which would make it 2 to the 6. There's 64 total outcomes under this scenario with those assumptions. Same thing's happening here. If we're going to guess on a 10-question multiple choice quiz where there's options A, B, C, and D, there's 4 options. So for each question, we're guessing 4 things. So I'll just write out question 1. There's 4 ways we could guess that one. Question 2, 4 ways we could guess that one. ... We could go all the way up to question 10, 4 ways we could guess that. So we're multiplying together 4 10 times. Yikes, that's a lot of ways. So how many outcomes are there? So the way to do exponents in your calculator, I don't know if you've done that already. I like Desmos for this. You do 10, and if you open up the little keypad, there's this A to the B thing, and it shouldn't be 10, it should be 4, raised to the 10th power. There we go. Yikes. That's a million ways, over a million ways you could, million guess combinations or a million outcomes. The other way, if you do Shift 6, there's that little caret button there. That's your other way of it's the shortcut for getting to an exponential power. And your calculator, your little basic calculators that your cell phones have, it's the X to the Y. I should glance, where is my cell phone? I think you might have to turn it on its side to get exponents, get the scientific. Yeah, there's not an option here. Okay, so that was 1,048,576. Yes, 576 outcomes. That's a lot of ways, a lot of options in our sample space. Okay, next one, you're gonna toss a 20-sided die and then a fair 8-sided die. By the way, remember, fair means each of those numbers are equally likely to happen. So there's a 1 in 20 chance for any number to show up here, and a 1 in 8 chance for any number to show up here. So what's the sample space, or the size of the sample space? Since we're just tossing one of each, it would be 20 times 8, which is 160 outcomes. So then Pennsylvania put the steam engine, the license plate had a picture of a steam engine followed by 4 digits. Assuming that repetitions are allowed, how many railroad memorial plates could be issued? Well, if you think about non-repetitious things, the numbers we could write is 0 through 9. That's a total of 10 options. And so if we have 4 digits, digit 1, digit 2, digit 3, digit 4, we're just doing 10 times 10 times 10 times 10. That's 10 to the 4th. And if you're familiar with how these work, that just means you have 4 zeros, 1, 2, 3, 4. So that's a limited edition license, only 10,000 of them. I feel like I'm like just cruising. Is everyone okay? So much easier in person when you do this because you can see people still writing. Okay, thanks for those, y'all. All right, so then now we're going to select 3 cards. For those of you that aren't familiar with the standard deck, I'm just going to quick jump to your reference sheets. We give you the information for a standard deck on page 265. So this is a standard deck with no jokers. Note there are 4 suits, 2 colors, 52 cards. That's the thing you got to keep track of. These are face cards. This is an ace, and these are numbered cards. So we are to do both things. We're going to write out the sample space. We're going to calculate the sample size, or yeah. How far up, Laura, do I need to go here? Okay, nice. Awesome. Okay, so with replacement, what that means, it's a super important concept. We're going to have that show up a bit later. That means we pick out a card, we look at it, we put it back in the deck, shuffle the deck back up, and pick another card. So if we're picking 3 cards, got card 1, card 2, card 3. If we're doing it with replacement, there's 52 options the first time, 52 options the second time, 52 options the third time. Because we never, the pool we're pulling from hasn't changed. That means we'd be at whatever that number is. I kind of don't care, but I guess we'll type it out. 52 to the third power, 140,608 combinations of 3-card draw. If you are a Texas Hold'em type of person, this is sort of what's going on, except when you play Texas Hold'em, that's where they draw 3 cards and then they do like the river and the other thing. They don't replace the cards as they pass them out. And that's how you get good at gambling, is you keep track of what cards have been played, and you can calculate those probabilities in your head if you have them all memorized, so you know when to bet and when not to and all that mess. So what happens without replacement, that means after the first card is dealt, we now have 1 less card to draw from. So there's only 51 options left in the deck to pull out. And then for the third one, there's now only 50 cards left to pull out. So it makes it a little, there's a few less options.
A, B, C.
What? Oh, I don't know what I hit. I turned on text something. Okay, so 132,600. Still kind of difficult to track all that, right? And if you have 5 people playing, after you've passed out the first card, there's a lot less cards, so it makes it a little easier to quotes card count, but not that much easier. Okay. That leads us to this large sample size thing. I don't know how you all feel. I might just skip this. What do you think, Cindy? Or should we go through it? Does this super help people?
I think skip.
Okay, perfect. Let's
Yeah.
go to summarizing it. So what happens is, what we're looking at there is this empirical rule. Is that the next section? No, that was in here. Is the difference between an empirical probability, I can't spell, and a classical probability. So in a classical probability, when you we'll look with the coin. When you flip that coin, there's a 50% chance it's heads or tails, assuming it's a fair coin. With an empirical probability, what you do is you collect data. And so while classically we know there's a 1 in 2 chance that let's say the coin lands on heads, if you start flipping a coin, you're not going to have 50% of your coin flips be heads in the first 10. You might have 4 heads and 6 tails, or you might have 7 tails and 3 heads, or something of that nature, as you're actually flipping and collecting the data. But if you keep doing that experiment over and over and over, and you flip a coin 1,000 times, you're going to get closer and closer to the classical probability. If you flipped it infinitely, you would have exactly half of your flips being heads and half of your flips being tails. That's the theory, and it is the reality. And this is an important note here. There is no such thing as the law of averages, meaning you're not, like if you've lost the last 100 times on your bets, that doesn't mean you're now going to win. The probability never changes no matter how many times you flip a coin or no matter how many times that little roulette wheel is rolled. The ball is going to land on whatever thing it lands on based on the classical probability, which is why if you go to a casino and they post the previous winning numbers, that is meaningless information. It's garbage. It doesn't help you decide what to bet now at all, because the whole board is reset and you start again, and each outcome has its same equally likely chance of happening. What does that mean for the gambling industry? They make money, right? It has to be that way. Otherwise, they'd have to shut down, and they have to pay their workers, right? And so they have to bring in money as you gamble. I guess this is important. I guess call the hotline if you have a problem, or only gamble the money you can afford to lose. How I like to think about this personally is I pay for internet sometimes to play video games. That's like money that's flushed down the toilet. It's entertaining. So if you go gamble, you could think of that. You could say, here's the $100 that I'm allowed to spend every month to gamble because I enjoy it. If I make some money, great. I can spend more. If I lose some money, well, that wasn't fun. Maybe I shouldn't gamble. I don't know. Cool. Any questions on all this? I should look at my phone. Cindy, were you wanting me to go through 5-2 as well? Or is that what you're doing?
Nope,
tomorrow?
we're doing that. We're going to do that tomorrow.
Perfect. Okay. Cool. So let's practice this mess. We're going to start with Cindy's worksheet first, which is the 5-1 worksheet 2 or 1?
Yes, actually, I have 5.1 worksheet 2. And for this week, you have 5.1 worksheet 3.
Okay. So we're going to do both of these now. But we'll start on page 545. And this is your chance, everyone, to demonstrate that you've got it. So let me do the reading thing. Okay, so we're told that there's this game that Heather is playing. Note, it's a probability experiment, meaning there's predictable outcomes that we know all the possible outcomes. We don't know which ones are going to happen, but we can calculate probabilities of them. So the game consists of tossing a fair die. Remind me, everyone, what does it mean to be fair? Why is this stated? Oh, that's A. Yeah, let's remind ourselves. What does that mean? What does it mean to be fair?
That it's equal on all sides.
Yeah, meaning since it's 6-sided die, meaning there's a 1 in 6 chance, a 1 out of 6 chance for any number to happen, for any number to occur. I guess we should say for the die to land on any number. Yeah, that's what fair means. Yeah. Now, Heather is tossing this die once and records the side facing up. And then she's got these different outcomes into specific events. So the event low is 1, 2, medium 3, 4, high 5, 6, even this, that. So we know that each of these, well, okay, let me stop talking. Yikes. I'm going to get some coffee so I can talk faster. And I want to see if you all can't do B through F. And we'll do 5 minutes. I'm going to grab my phone and you all try this. How are we doing, y'all?
F has got me stumped. Because it wants both, right? It wants the result that is low and it's also even.
Tricky.
So do you write two separate ones or is there some combo that's coming down the pike that you do?
There
for?
is a combo that's coming down the
Okay.
pike. So what you could do is think, well, so, oh, yeah, no, that's tricky. So what are the chances that a result is low, is also even at the same time? So let's see. Low was defined as 1 or 2, and even is defined as 2, 4, 6. So how many outcomes are both low and even?
1.
Yeah, it's the number 2. So that, I believe how we would write this, it's a little, the language here is a little wonky to me, is we would write it like this. And the answer is 1 out of 6. Because it's just that 2. Is that what you were thinking?
Yeah, no, that's actually much better than what I was thinking.
Okay.
I was trying to
It-
overcomplicate it.
Well, this stuff, it's all about the words. I think the problem, like the calculation itself is pretty straightforward. It's just one number divided by another number. The tricky part is determining, well, what is this number? And that's all about, like, did it say and, did it say or, did it say blah, blah, blah? Yeah. Okay, what'd y'all say for the sample space? Let's make sure you all got this.
Don't be shy.
Yeah, don't be shy. And
I
if you
did-
don't know, tell me. Yeah, go ahead,
I did
Nicole.
1, 2, 3, 4, 5, 6.
Nailed it. That's it. So when we say sample space, that means what are all the possible outcomes of the probability experiment? What was the experiment? Roll a die. Roll a 6-sided die, I should be clear. There are multiple different sided dies. Okay, so what's the probability of getting a medium result? So I'm just going to put probability of medium. This is the notation. What'd you all say?
1/3.
1 out of 3.
Nailed it, you all. Excellent. There are 2 outcomes in medium. So there's 2 ways we could get medium. There are 6 total outcomes. If we want to simplify that or do the reduced fraction, we'd write that as 1/3. I'm not super picky about reduced fractions in Desmos. There's this little fraction button here. So if you didn't know how to simplify or reduce to 6, you would click this button, oops, and it does it for you. I'm not concerned. I mean, this one's probably not too difficult. Most people can do this one. Divide top and bottom by 2. But if it gets like crazy complicated fractions and it says reduce them, just type them in here and click the fraction button. And Desmos will do it for you. Okay, what'd you all say for getting even?
One out of 2.
Yeah, nice. Yeah, it's okay if it feels easy. That's great. If it doesn't, that's okay too. There are 3 possible outcomes in even. There are 6 outcomes total. 3 out of 6 is 1 out of 2. How's everyone doing with this? Are you getting the structure of how to calculate the probability? Outcomes in the event divided by outcomes in the sample space.
I think I'm having a hard time because there's 2 sets of numbers.
Talk to me about which ones are you talking about?
All of the numbers.
So let's see. Were you good with this set of numbers?
Yes.
Is it the fact that the outcomes are numbers themselves? Is that part of it too, maybe?
Probably.
Because if it was like male, female, or something else, that yeah, I might not feel as crazy. Cool.
Okay.
So when you see these little brackets, what you're interested is not the numbers necessarily that are in them, it's how many are in them. Even has 3 outcomes, odd has 3, high has 2, medium has 2, low has 2, our sample space has 6. So any calculation we do, there's going to be a 6 on the bottom, and then we're just going to say an event. Like here's one. What's the probability we roll a 1?
One out of 6,
Why did you say 1 out of 6?
because there's only one number 1 out of
Good.
the 6 numbers.
What if I put a 5 here? What's the probability of rolling a 5?
Still 1 out of 6.
Perfect.
Because
Misty,
there's
is that
only 1 5 on the die.
yes? Is that helping, Misty?
Yes, it does. It did.
Because I've
Oh,
seen
sorry.
students that
Sorry, Misty.
No, you're fine. I got it.
good. I mean, I've seen students that rightly make the thought of, oh, I should put a 5 out of 6 because what's the probability of a 5? Well, that's the number 5. Let's put it on top. I get how that can get tricky. Okay. Are any of the events that Heather defined simple events? Do you remember the definition of simple events?
So do you guys remember that it can only have one outcome?
Well, if you're looking for one particular number,
Good.
like if it was a dice that just had zeros on all of it, wouldn't that be no matter which side you rolled it on, you're going to get a 0?
You're thinking too deeply on this one.
Oh, okay.
Event is there only one thing in the brackets?
So the answer would be no, because
look-
you can always get more than one option.
Yep. No, because her events had 2 or more of. So here's Heather's defined events: low, medium, high, even, odd. They all have more than one outcome. This is a simple event. Probability of rolling 5. Yeah, it's easy to overthink this stuff. Very easy. Because you're like, oh, this is super complicated. I've never seen this in my life. And then it's just brand new. That's all. So we'd say no, none of the events have only one outcome. They all have 2 or more. How'd you all do with number 2? Or did you even do it?
I put there's only a 45% chance of rain tomorrow.
You got it. 45% chance of rain. That's making sure you get, when you see this P parentheses thing, that stands for, in the stats world, probability of whatever's inside. So this thing in here is called the event. Yeah. Okay. So how about I give you 5 minutes? That's probably not enough time, but we'll do 5 minutes, and let's see how you do on page 2, numbers 3 and 4. And before I go crazy on turning you loose, are there any questions on what we've just done? Set a timer for 5 minutes. Okay, that was 5 minutes. Do we need more time?
Do I need just one tree or do I need two because he's there for 2 days? That's what I'm caught on.
Gotcha. So the hospital menu has 4 equivalent desserts for patients. Jake is in the hospital for 2 days. You need 1 tree because what we're going to do is the sample space for his entire stay. So you're going to think, here's my starting spot. And this is going to be day 1. And then you'll have some branches off there. And here's your second day after your branches.
Thank you.
And it's just the desserts. Any other questions?
Do the trees all have to start with just the 2 branches, or because there's 4 options, you can have 4 branches, which denotes your, okay, good. Because mine was looking kind of crazy, but I just wanted to make sure.
You got to have 4 because
Yeah.
you're the first choice. There's 4 options for that branch. Yeah, good question.
Okay, cool.
Maybe I give you another 5 minutes to draw if you'll need it. How about tell me when you're done? 5 minutes. Go ahead.
I missed this when you explained it earlier, so I can wait for all of us to go through it. That's fine.
I'll scroll back up here. No, I won't. That's like miles away. 145. Let's guess it's that page. Fail. Here was the picture we drew. Oh, look at that. I bet you can get it just by looking at it, right? Thanks. Let me clean it up. Oh, fail. Oh. Does this help at all, Laura, looking at this? Set a timer for 5 minutes.
I'll review it. Thank you.
How about we just draw it? Taylor's asked that we draw it, so we'll stop the timer. Oh, she canceled it. Look at that. Where were you? 5.1 worksheet 1. Worksheet 2. Okay, so what happens is we start with our 4 options that could happen. They randomly select a dessert for patient Jake, and it could be cake. Let's hope that's what it was. Could be pudding. I would throw that away. Could be Jell-O. Or it could be ice cream. Okay, I'd eat that too. So those are the 4 options on day 1. If we didn't have a second day, it would be a 1 in 4 chance of any one of these happening. Does that look like a J? Maybe. So on day 2, this is where it gets crazy, right? Because then if we had a cake, we now have again 4 options. We could get cake again. Hooray. We could get pudding. Boo. We could get Jell-O. Kind of boo. We could get ice cream. It's okay. And look at how awful this is. I've already not drawn it with enough space because I need 4 more things here. And then I need 4 more things here. And then I need 4 more things here. And it's just like, ugh, let's start over. And don't worry about these being super pretty. Remember, the goal is actually to create the sample space. Although this just says depicting the sample space, I think the best thing is being able to create it. So let me try again. I need a lot more space. So here's 1, 2. Oh, that's. Ooh, let me try again. Whoop. That one. That one. Oh, I've seen it done this way. You do cake, pudding, Jello, ice cream, and then draw them in. That's not going to work very well either. Whatever. We're going to call it good. And then
I
cake.
went straight up and down, and then 2 branched out, and it fanned out perfect.
Nice. Okay. I'm committed to this failure. Oh. Doop, 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 doop. Do you want to, I was going to say, do you want to show us yours? Look at how bad mine is. Oh, this is awful. There's a person called Vihart, V-I-H-R-A-T, that like draws this stuff for fun. She's a musician and mathematician. Super cool. Can anyone tell me the size of the sample space?
16.
Nailed it. You were very hesitant. How did you guess 16? I don't think you guessed. How did you know 16?
Because when I wrote down what all the choices were, well, that and it's 4 to the 2nd power.
You got it. 4 choices for the first one, 4 for the second. We're going to end up with 16. Or you could count your tree. Nailed it. What does the sample space look like? CC, CP, CJ, CI, PC, PP, haha, PJ, not funny, PI. Right? So this is what it would look like if we had to write the whole thing out. This is the start of it. Does that help you all? Are you feeling better or is it worse?
Sounds good.
Okay. So I'm gonna have to erase this last branch. And let's see, what's the probability that Jake's receives cake on the first night and then pudding on the second night? Notice that order is probability of cake and then pudding. How many ways can that happen?
Once.
Only one way. Yeah, only one way. So that's a 1 out of 16 chance. And we said we want a decimal. So it's
0.065.
You got it. Why am I doing approximately? It's exactly equal to, come on now. Exactly equal to 0.0625. If we wanted to think about that as a percentage, you'd multiply by 100. There's a 6.25% chance he gets cake and pudding. Okay, get ready. Would it be unusual? Pause. What's the definition of unusual? This is old school stuff.
Is that the 0.5 or something of that sort? I was wondering where in the notes it was. I was trying to look it up and I knew it had something to do with a 5. I just couldn't remember if it was like 0.05.
It has to be less than 5% to be unusual.
It showed up with the empirical rule back in chapter 3, right? We had 2 definitions. Are we more than 2 standard deviations away from the mean for that data value? Or is it a less than 5% of the data values? What we didn't tell you back then, or maybe we did, or we're about to, is that the area under that curve is probability. So when we say 5% is the threshold for unusualness, we're now saying, is the probability of ice cream less than 5% or 0.05? So what we need to do is calculate what is the probability of Mr. Jake getting 2 ice creams in a row or getting ice cream both nights. Anyone know that?
I got 0.125.
How'd you calculate that?
It'd be 2 out of 16, which is 1/8, which is 0.125.
How do you get 2 out of 16?
Because choice 1 and choice 2.
But
Well,
it's for both nights, right? So the experiment is the 2 nights together.
Oh, I gotcha. Okay. So I got
Very, very reasonable thought to make, by the way. You're not far off.
so it's the same as actually, then it's the same as B then.
Yeah, it's exactly the same as the one above. because each outcome is equally likely, any two desserts together, it doesn't matter what the desserts are, there's a 6.5% chance, or 0.0625 chance. So is this less than 5%? And our answer, of course, is no. So is it unusual? No. The probability is not less than 5%. Good. Good, good, good. Questions on this, y'all? Ooh, grounds. Ooh, delicious. Anyone write this down? Letter 3, number 3.
P parentheses 18 equals 120.
Nailed it. I think you meant 1 over 20, right?
Yes, one
Yeah,
over
you're good.
20.
I knew what
This
you were thinking.
math is so much easier than the other math we just got out of.
Oh,
Like, I like this math.
that's wonderful. I hope everyone else shares that feeling. If you don't share it, no worries. Talk to me. Reagan, what you got?
I wrote down there's a 5% chance to roll an 18 on a 20-sided die. Should I just write down the easier thing?
Well, yes, this is what we're looking for because we wanted
Okay.
probability notation.
Okay.
You wrote a nice explanation of what this is saying. I think it's easier to understand, for most people, I think it's easier to understand a percentage than a fraction. Yeah, good. Okay, so if it's feeling easy, excellent. Let's prove it to ourselves by doing worksheet number 3. Of course, we're going to throw some crazy stuff at you, so don't feel bad if this gets tricky. This is page 547. So let's be clear. This worksheet we just completed is for Cindy. This is your 033 one that is due on, I think, Sunday, 10/2. And then we're now gonna do the one for me, or 133. That's worksheet number 3. And this is also due 10/2. I mean, we're gonna do the whole thing now, so whatever. But so let me give you 5 minutes to just taste this and see how you can do. Yeah, if you are getting stuck, like if you can't get started, tell me so we don't have to wait all 5 minutes. Set a timer for 5 minutes. Talk to me, Taylor. What does that mean? Oh, about what? I'd love to help you. Something up here or this down here? That is super common. You will start to correct that the more comfortable you get with it. So you are not alone. That's a very common thing to happen. So what you're going to start to do is create these neural pathways that when you see words like outcomes and sample space, you know you're looking at this graph and you're going to write all of the unique things that this arrow could land on. For example, one of the things this arrow could land on is the number 1. It occurs a couple times, so we only need to list it once. What else could it land on? Is that enough to get you started? Okay, good. Is that all of the things it could land on? You make sure you filled in every possible thing, every unique item that this could be. Okay, okay, good. Keep going.
So I have a question. So we have the little spinner there, and it's got multiple times that sum's landed on it. And maybe I'm trying to overcomplicate it, but we've got the sample space, which it's got to be one of those four. But if they're on there, like for instance, there's 13 spots that you could land on.
Nice.
So would that be so? Like for instance, B, when it's talking about the discount coupon and stuff, wouldn't it be whatever it is out of 13 then, or is it out of the four, the sample size?
Great question. Oh, that is such a good question. And I am trying to think how best to answer this. Okay, so this are the list of outcomes. And we didn't write the repeats. The sample size, the size is 13 because there's 13 things it could land on. It's just that the one comes up, has a 2 out of 13 chance of happening.
Right.
So I guess the point we should make here is that these outcomes are not equally likely.
Okay. Because
That's a
that's what
really
I had first was 13, and then you started writing 1 through 4. So then I got a little back confused, but that makes sense if it's unlikely because they're not exactly even. They're not, it's not fair.
Yeah, which
Okay.
which makes me think that maybe when we list the outcomes in the sample space, we should list the 2 ones, but in reality, we're not going to make a distinction between which of the ones did we land on. Did we land on this one or this one? It's just, it's on a 1, so you get $10. Hooray. Yeah, good question. So my buzzer went off. Do we want to talk about things or do you want some more time?
Would B be 10 out of 13?
Great question. So we want a 3 or a 4. So how many 3s and 4s? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so there's 10 ways that they could, or 10 spots that have a 3 or 4 on them. There's a total of 13 spots. Yes, so the probability of a discount is this, which is equal to 7.769. So most likely, right, they're going to get a, nailed it. You're going to get a discount coupon. What'd y'all do for C? You said no, not unusual. How many 2s are there? 1. So it's a 1 in 13 chance. I don't know what that is as a decimal. Ooh, 0.769. Yep, not unusual. So we're explaining how we would explain is you could say this. Don't write that. Come on. Good. Does it feel like it's getting better? So no, because 0.769 is not less than 0.05. Taylor, how about you? Is that feeling better or worse? Oh, wait, you answered that one, so it's feeling better. Yay! Oh, look at that. Just one problem later, and you're already doing better. How'd you all do with number 2? This is kind of old school stuff. This should look familiar to you. It's a frequency distribution. Do you remember what this means?
Some.
Good. So look, remember what used to be here? Relative frequency, which was the percent. But now we're like, oh, guess what? It's a probability. Surprise. We tricked you before. Not really, but kind of. So yeah, you're just filling out the probability thing is just the relative frequency. Wow, we do not have a lot of people in the military. That seems like a tiny amount. Little tedious, right? Because you got to divide all these things here. Let's do it this way. All right. How many decimals are we supposed to give? 3. We all feel good about that? Is that okay?
That's the stuff that I really understand. I got that. Chapter 4 was a disaster.
Well, chapter 4 is tough. Don't you give yourself some slack on chapter 4. Chapter 4 is heavy algebra. Okay. Let's set the timer for 5 minutes again. Oh, don't hate, appreciate. Think of it as a challenge, right? You get to push your understanding of something, and then when you get it, you're gonna feel so good. You can still dislike it, but you're gonna conquer it. It's yeah. Okay, so let me do 5 minutes. This one is. Does everyone remember what you need for a valid probability model? There's 2 criteria you're looking for. I'm going to write the criteria in super gross notation. And then you all can see if that reminds you of something. So that's the 2 criteria, most definitely. I'm going to set the timer for 5 minutes. Is that far enough, Taylor? Do I need to go higher up? Okay, good. I'll set the timer for 5 minutes and let you work through this. There are 3 questions you need to answer here. So you need to answer whether these are valid for each one, yes or no. And if no, you need to explain which of the criteria failed. This is all about language connected to numbers. Okay. I'm sure you looked at that number line going from 0 to 1 with 0.5 in the middle. And so things, 1 meant certain, 0 meant impossible, and 0.5 meant equally likely. And then if you're on this side, it's more likely to happen than not. And if you're on this side, it's less likely to happen than not happen. And then I'm going to remind you of one thing in a box plot. Actually, I'm going to ask you to remind me. What % of the data are between these two red marks that I just made?
25.
25.
Good. You chapter 3. Hooray. Okay, you're going to use that. That's a percentage, which is a probability. Okay, so let me get out of your way. Taylor, did you have enough time up here? Okay, so let me get out of your way. You take 5 minutes and see what you can do, and then let's talk about it. Set timer for 5 minutes. How we doing, y'all? More time, less time, questions? Stuck, not stuck? Everyone sleeping? Did y'all take a break like I did? Push-ups? Talk to me.
I'm stuck on the bottom, but I think I might have it, but I doubt it.
What'd you say for A?
That's the one I'm trying to figure out because I'm not sure, because I know you had the quartiles and stuff, but I wasn't sure if I was looking at it wrong and again trying to read too much into it or not. Because I was thinking if it's the one, then it's about midway. So
Okay.
because the medium right there, so wouldn't that make it 2 out of 4, which would be half? So the
You
probability
got
would be-
it.
Oh,
Mm. It's okay. You can flex a little.
maybe I'm
Muscles.
getting it. I'm just trying to overcomplicate it in my head then.
You got it. You crushed it. So what you're supposed to note is that each of these, exactly what you said, they're quartiles, right? So Q1 is that little tiny whisker right here. Q2, I'm sorry, Q1 is right here, and then this first quartile, that's 25%. Here's 25%. Here's 25%. From here all the way to this end is also 25%. And so it's half. You had to note that 18.5 was at the median, and so it's these two together, which is 50%. Nailed it. That feels good. How about the rest of you? Did y'all feel good about that or not so much? It's maybe my 4th cup of coffee. I don't know. Did you feel good about this being 37 million Instagram users? Okay, okay. So Reagan, what did you say for B then? What's that probability? By the way, I'm wrong. Since it said more than, it is not the 2 I circled that make the 50%. More than are these 2. Same answer, but it was the wrong 50%. I wouldn't have known the difference if I was grading, but I want to make sure that that's clear to you all that the words more than meant these 2 whiskers. And here where it says less than, it's this way. So what is the probability we select a country that has less than 37 million users? What would that be?
75%.
Because it's 3 quartiles. Yeah, so that's 75% of the data is within that range. So there's a 75% chance when we randomly select a country out of this data set that they will have less than 37 million. Yeah? No? Too much coffee? Not enough? How'd you all do with this mess?
Had to use one of the descriptions more than once.
Good, that gets everyone every time. It does say that you can use them more than once. It's a mess. Okay, well, let's talk about it. Point 5. It is as likely to happen as not. Do we feel good about that one?
Because that's the closest thing to say it's fair.
Yep,
Or equally
fair,
likely.
equally likely, as likely to happen as not happen. I know the language here, it is wonky. Okay, and then B, 0% chance of happening. It's not gonna happen. It cannot happen. It's impossible. 0.9. There's a 90% chance it's gonna rain today. Are you taking an umbrella? I said 4. It is very likely to happen, but it is not certain. So 10% chance you don't need that umbrella. How about 1?
Number 1.
Nice. Sorry, stole your thunder. Good, good, good. It's going to happen. 100% chance of rain. 10% chance of rain. It's not unusual, right? Because it's not less than 5. It may happen, but it's not particularly likely, right? In fact, it's super unlikely to happen. There's a 90% chance this won't happen. How about negative 0.25?
It can't happen.
Nailed it. Yes. There's no such thing as a negative probability. Like if it can't happen, what's a negative 5% chance of it not happening? Right? Like how do you get, I don't know. It doesn't make sense. Okay. Ooh, 0.01. How does that make you feel?
I took a wild guess and said it was unusual for this event to happen.
So why is that a really good wild guess?
Because I didn't think any of the other ones fit.
Nice.
It's less than 5.
Yes, right? When you see this word, there should be 2 things that immediately pop into your head. 2 standard deviations away from the mean, number 1. If we know standard deviations, this isn't anything about standard deviations. We don't know means. We don't know any of that. Doesn't even really apply. So it's that or less than 5% chance, which as a decimal is 0.05. So that's the thing that crops up. Yeah, it's unusual. 4 is also a legitimate answer. It's very unlikely to happen. It's not, but it's not certain. Wait, I'm sorry. It still may happen, but it's not likely. It's just highly unlikely. That's why we use 5. That's the better answer. And of course, 2, you can't have a 200% chance of something happening. Once you know it's happening, once it's certain it's happening.
I said someone made a mistake.
So yeah, someone made a mistake. Oops, why did I put a 6 there? These are both wrong. These should both be 7s. I'm sorry. I feel like the numbers, I don't know, whatever. Okay. Anyone not happy about that language? Would you all say for the first thing here? Is this a probability model or not?
It didn't equal to 1.
Okay, no, because the sum is not equal to 1. So, right, it has to add up to 100%. These have to add up to 1 in order for it to be a model. And so you added them and you didn't get it. So you could say, no, the sum of all the probabilities is not equal to 1. Good. How about the second one? And if you like words, you can use words. Sum of prob not equal to 1. You said yes. Okay, good. Don't let this outcome bother you. You can have negative outcomes. You just can't have negative probability. So that one's fine. It adds up to 1, and each probability is between 0 and 1. How about the last one? Why no?
because it has a negative probability in the table.
Good. You can't have a negative probability. This doesn't make any sense. What? So no, we have a probability that TH is equal to negative 0.18, and that is not possible. Good. Okay. How do you feel about drawing in the next 10 minutes another sample space for guessing 4 true and false questions? Gross. Nice, Nicole. Yeah. Negative probability.
Eric,
have
they mentioned to me yesterday, they want a whole midterm of the probability table.
Okay. You just want the midterm to be just like these tables over and over and over?
Yeah, throw chapter 4 out.
What if I have, I was gonna say, what if I have, well, yeah, no, chapter 4 is gonna be there. Sorry.
Dang.
Oh, come on. Make it like 3 questions and be done. I'm gonna twist your arm.
It's like 1 page.
Okay, fair
It's
enough.
2 pages.
That's fair.
It's 2 pages.
That's fair.
And what you'll do on the midterm is you'll find a model from a data set. You'll tell me what the slope is and what it means. You'll tell me what the y-intercept is and what it means, or whether it doesn't make sense. You'll plug in an x value to the equation to spit out a y value. You'll subtract the y value that you got from an actual data value that I hand you, and then you'll tell me whether that's an overestimate or underestimate, and you're done. You'll also tell me the strength and direction of the correlation.
Okay.
That's it. That's all it's going to be. And I
Okay.
know you hate all that, but you know,
Praise God.
and you might interpret an R squared value. Basically, what's going to happen to you on the midterm is you're going to do all of these things. Right? You're going to interpret, or you're going to gauge a strength and direction from an R value you have. You're going to interpret the R squared value that you got. You're going to somehow generate an equation or be given an equation and tell me the slope and the y-intercept and do a calculation and then do a residual calculation. So there's no surprises of what's going to happen. You just have to practice until you feel good about it.
Okay.
Yeah. And like, if you can read this, I'm pointing at the screen. If you can read what's on this, if you can read this and you know how this is all done, you got it. We're not going to trick you and be like, oh, nope, you should have used on mean instead of average. No, you just write that. You all got it. When that midterm comes, I'm just going to push you right off the cliff and you're going to soar. But just don't hit the sun, because we don't want to melt the wax on your wings.
Eric, can you verify that they can begin their midterm at your office hour at 8:30?
Oh yeah, sure. Oh, I forgot. Oh, that is a challenge, isn't it? Yeah, so we'll have 2 options. You can come in the morning at this time, and you could, so from 8:30 till 1, you could take the midterm, or you could come in the evening hours and you could go from 6 until the next morning, or however long you want it to take. Because my evening class, I have nothing other than going to bed.
I told them until Eric's bedtime.
Which some nights is 10, some nights is 2. You know, I'll stay up for you. I'll just like build Legos or something.
Are you standing and not sitting in a chair?
Yes. Yes, this is, I have a Lego desk thing here that it's like my workstation. And so, yes, that's why I'm dancing. I do have a stool if I get tired from standing too much, but you know, this way I can do like squats. Ooh. Okay. Too much coffee. We got 6 minutes left, and there's 1 question left on the worksheet for my class. I want to think you can do it. Let me just get you started on the sample space. There are 4 questions you have to answer, and there's only 2 outcomes for each question. So you might kind of start with question 1 and branch it nice like this, and then do false and true, and then keep going, right? You need Q1, and then Q2, Q3, and Q4. And in the end, what I'm really looking for is that you've written out the sample space. And one of them, if we finish this one off, would be false, 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 false. Quick question, how many outcomes will there be in this sample space?
16,
How'd you get that?
4 times 4.
Technically, you did 2 times 2 times 2 times 2. But yeah.
Okay. Yeah, I did. That's how I did it.
Yeah. So and the 2's raised to a power are the weird ones, right? Yeah. So it's because there's 2 options for each question. There's 4 of them, so it's 2 to the 4th, or 4 times 4, total of 16 outcomes. Cool. I think I'll let you all do that. And if we need to look at it in class on, what is it, Wednesday? On Monday, we certainly can. 5.2 and 5.3 are going to add to this stuff. So it gets a little more complicated the further we go. You're going to have to start being able to tell the difference between and or. So I think it's really good to make sure you have a solid understanding of this more basic beginning level. And that is, the probability is an amount, the number of outcomes in the event divided by the number of outcomes in the sample space. That's like the big take home, because then we're going to start messing with that. What if we want both events to occur at the same time? Or what if we want an overlap? So yeah, I don't know what else to say there. Any questions that you all have for me in the last 4 minutes here? The midterm is scheduled for, let's see, I know it's the 18th. So for us, it would be the 17th. And Cindy, correct me if I'm wrong. What I'm going to do is email you the exam, and then you write your answers on paper. And then you submit a photo of your answers into Canvas that I grade.
You are correct.
Talk to me, Reagan.
Would we be able to come in person and do it? Just because I think I probably would do better, like if I would be on campus or whatever.
Yes, so there's 2 ways we can have that happen. There's a testing center that I would just give you a window of time that you would have to take it by, and I put the exam there, and you can drive into campus and go to that testing center and take it. Or I am administering this same exam in my in-person class on the 18th in McDivitt, and it's at the same time as this class. And there's only 15 students, so there's plenty of space. I think just let me know so I know to have a copy of the exam.
Okay, thanks.
And if you want to, if anyone, and this is for anyone, if you want to take it in the testing center, let me know that too. You have to, I think you'll have to schedule that. My only fear with those things, and for anyone, is someone not taking the exam at some point. So that's, as long as everyone takes it, we're good. That's a great question. I think usually the exam is about the same length as the sample midterm exam, actually a little bit shorter. So in past times, it's been 10 pages long with 5,000 questions. No, I don't. It's usually like 10 pages long, spaced out with maybe 10 to somewhere between 10 and 15 questions, where there's parts A, B's, and C's for many of them. And when I say 10 pages, I mean 5 pages front and back. When you get a digital version of it in Word, it would be a Word document with 10 pages on it. And then average time, oof, that's Well, that's tough. I would say typically students, typically, listen to the stats language, fit a single class time. So
So
that's,
usually about 2 hours.
yeah. I think we try to write it for the hour and a half range. For the middle of the road student, taking about an hour and a half. And then there's some students that do it in like an hour, and then some students that do it in like 10 hours. I don't
Do
think
not
anyone's
be
taking 10
scared.
hours.
Do not be scared.
Yeah, we're gonna dispel that, Taylor. We're getting you there. So here's the reason you don't need to be scared. Every question on the midterm, if you've done the worksheets and the reviews and the sample midterm review, you will have done every single question. And this is where Cindy and I are always a little concerned when like we do the problems together. That's great for learning. That's not good for practice. To get rid of that fear, you've got to do it by yourself with no help and prove to yourself that you know how to do it. And so we're trying to help you get to that point. Yeah, awesome. I love to hear that. It does ask it in a different way, which makes it so that you have to really understand what's going on. So if you're doing that without help, don't be scared. You got it. Okay, y'all, I got to get to my next class. Great work. We'll see you on Monday. You'll see Cindy tomorrow with 5-2. And have a great weekend. Don't be afraid to ask questions.
I'll see you tonight, Eric.
Sounds good.